looks like this. This is week 8, which is sort of hard to believe. So today, I'm going to talk about section 8.2, which is about solving homogeneous, constant coefficient, linear homogeneous equations. Tomorrow, I'm going to talk about 8.3, which is about non-homogeneous equations, but it's a lot more fun just to do those than it is to like watch me talk about it. So I might just give you, I'll briefly talk about it, and then we'll just solve a bunch of problems. On Thursday, we will do sort of our typical sort of exam prep. So exam prep lab day. I am covering like 3 or 4 additional hours of class today because people are out sick. So I have not had a chance to go to my office. So if you have emails from me to me that you're waiting on me responding, I just haven't had a time to get back to my office. I will post a mock exam sometime either tonight or tomorrow, and then I'll have a different one to do on Thursday. And then on Friday we will have exam 2. And then for the rest of the quarter, I promise it won't take me 2 weeks to get the exam back. That's the first thing. And then in week 9 and 10, we're going to be talking about chapter 9, which is about systems of equations. Equations. And then we're also going to talk about the mass spring system, which is everybody's favorite differential equation. That's section 8.5, and we'll be set up to do that next week as well. That's the basis for studying all kinds of vibrations and circuits and all kinds of things. So what we're going to do today is we are going, I guess the last thing administratively, because I've been called in on an emergency gig to cover a professor's class at 2, and I'm usually at my office hours from 2 to 4. I'll be there from 3 to 4 today if you want to come by the breezeway. Not a lot of you guys have come to visit me, but if you do, I will be there from 3 to 4. All right, so today we are talking about 8.2, which is, see, here's what you do in differential equations. You just put enough adjectives on the problem so you can actually solve the problem. So 8.2, we're going to talk about constant coefficient linear homogeneous differential equations. And if we're going to go one step further, most of these are going to be second and third order. Because the solution to these guys is going to involve factoring, and once you get above third order polynomials, factoring is hard. Actually, for some people, factoring third order polynomials is hard. Probably not you guys, though. Okay, so the basic observation here, and the method that we're going to use for this entire thing, is that if I have a first order equation that looks like this, y prime plus ay is equal to 0. By observation, y prime is equal to minus ay. By observation, you can see that the answer here should be y is equal to e to the minus ax. Right? A first order equation of that form has exponential solutions. So the approach that we're going to take to higher order equations is to assume, and this is not an assumption, this is true, that all of the solutions to a constant coefficient higher order linear homogeneous differential equation are some kind of exponential, always. So generally, we're looking at equations. I'll write down the second order version. ay prime plus by prime plus cy is equal to 0. This is what we mean. I guess I should say further, a, b, and c are constants. This is the general form of a second order linear differential equation that is homogeneous with constant coefficients. So if we choose a trial solution, we make the assumption, hey, wouldn't it be great if second order equations had exponential solutions just like the first order ones did? So as a trial solution, you try y is equal to e to the rx. Assume that's a solution. What form must it have? If you plug that into the differential equation, a times r squared e to the rx plus b r e to the rx plus c e to the rx is equal to 0. You factor out the e to the rx. Well, e to the rx can never be equal to 0 because it's an exponential function. So we can just discard it. We can divide both sides by e to the rx if you like. And what we land on is the equation, this is a solution if this equation is solved. Br plus c is equal to 0. So this guy right here turns out to contain all the information that we want to know about the structure of solutions to a second order linear constant coefficient homogeneous differential equation. So we started with a y prime prime plus by prime plus cy is equal to 0, and we arrived at a r squared plus br plus c is equal to 0. So this guy right here is called the auxiliary polynomial. Although in many contexts, it is also called the characteristic polynomial. So if I accidentally say characteristic polynomial, I apologize. And you should notice here, you could have, without going through this thing with the trial solution, you could have just leapt straight from the differential equation to the auxiliary polynomial. The powers of r correspond to the order of that derivative, right? So the r squared term is the second order term, and the r term is the b term, and the constant term is the no derivatives term. So the structure of solutions to quadratic equations will reveal the structure to anything like this as long as we can factor. And so we're going to consider different ways that this type of quadratic can be solved. And why the quadratics? You guys love the quadratic equation. So essentially, there are three cases. So ar squared plus br plus c is equal to 0. The roots come in three varieties. Three flavors. One, they could be distinct. So that is to say, it could be that the solutions to ar squared plus br plus c is equal to 0 are distinct integers. Not integers, distinct numbers. They could be real. So R1 and R2 are real numbers, but not equal to each other. Distinct real roots, I should say here. Okay, in that case, because we've assumed here, as an assumption, lingering, even if you skip the part where you use the trial solution, as soon as you write down that auxiliary polynomial, you are making the assumption that solutions have the form e to the rx. That means as soon as you write this down, you're saying this is a solution if y1 is equal to e to the r1x and y2 is equal to e to the r2x. To give a specific example here, we did a bunch of this last time. That would be like saying if you have the equation y prime, let's do this one, how about 2y prime prime plus 3y prime plus 1y is equal to 0. You verify that it is a constant coefficient linear homogeneous differential equation, which it is. You convert it to its auxiliary polynomial, 2r squared plus 3r plus 1 is equal to 0. So that's the auxiliary polynomial. You solve it. Immediately, of course, because everyone's factoring is top level. So r is equal to minus a half, r is equal to minus 1. These are distinct roots. They're distinct real roots. And so from here, we could just immediately leap to the idea this has two solutions. y1 is equal to e to the minus 1 half x, and y2 is equal to e to the minus x. This case is particularly easy to show just in the general setting that these things are linearly independent as well. So note, if R1 is not equal to R2, then the Wronskian of e to the R1x, e to the R2x as a function of x is the determinant of e to the R1x, R1 e to the R1x, e to the R2x, R2 e to the R2x, which is, after you calculate, R2 minus R1 e to the R1 plus R2 x. If these are not equal to each other, this can't ever be 0. If R1 is not equal to R2, then that's not a 0 number, that's never 0, so this is never 0, which means they are linearly independent. And so the conclusion is the solution, YH, the general solution to the homogeneous equation, I put in the H down here for a reason. YH, the solution to the homogeneous equation is C1e to the R1x plus C2e to the R2x. Or in this case, specifically, YH is equal to C1e to the minus 1/2 x plus C2e to the minus x. So the distinct root problems are the easiest. The next thing I want to point out here is that this extends very easily to higher dimensions. The book basically just says, trust us that this still works because it's annoying to prove these things are linearly independent. But if I give you more roots, so I write down a constant coefficient linear differential equation, Ly is equal to 0, where L is constant coefficient, linear. And suppose you had an auxiliary polynomial that looked like r minus 1, r plus 1, r minus pi, r plus 1,000, r minus, 6 is equal to 0. So you wrote down a characteristic polynomial and you factored it. Then you can just read off for each of these distinct linear roots. See, R1 is 1, R2 is minus 1, R3 is pi, R4 is minus 1,000, R5 is 6. They each occur once with no multiplicity, so the general solution here is going to be C1 e to the x plus C2 e to the minus x plus C3 e to the pi x plus C4 e to the minus 1,000x plus C5 e to the 6x. You can translate the linear terms directly into solutions in this way. You generally will not be asked to verify that these are linearly independent, outside of just 2, because I don't want to read you guys do determinants. It's not very exciting. Okay. Any other point I wanted to make about that? Okay, so another thing is, as a working engineer, scientist, or mathematician, oftentimes you are less concerned about the exact picture of what the solution does and more concerned with its behavior, its qualitative behavior. So it's a theorem, actually, that every linear differential equation with constant coefficients is solved by exponentials. And what that means is you can read off from the values of the roots of the characteristic polynomial if your solution is going to blow up or be cool. So when you do this, you can see this term and this term. If you think about x as time, as an independent variable, those contributions disappear as time goes on. These basically limit to 0. These do not. So if you're designing some kind of physical system which has a corresponding differential equation, and you get terms that have exponentials that explode, you either got to redesign your system or figure out a way to choose your values of C1, C3, and C5 that you don't have things ripping off to infinity. Right? The qualitative analysis of the solution is often just as important as the actual answer when you're doing these things. And we'll look at this more closely when we talk about complex roots in a second. All right, questions about this case before we go on to the next one? Yep.
What does it mean if 2 of your roots are, or if two of them are linearly dependent? What does it mean?
What would it mean? It would mean that you didn't have enough solutions. So if this was a fifth order equation, 5 different answers would be enough to build a span that got the entire solution space. So if you had some were linearly dependent, it would mean that you didn't have enough information to capture the entire set of solutions, right? So that's another thing that shows up in practice. If you're solving a 4th order differential equation and you come up with 3 solutions, there's an entire dimension of information that you've missed and can actually affect the problem that you're working on, right? So you want to make sure you have enough independent pieces of information to completely describe the solution space. All right, let's look at repeated roots. Because that's the next thing that could happen. All right, case 2. Repeated real roots. So it's possible that you could have AR squared plus BR plus C is equal to 0, that when you factor it, you end up with R minus R1 squared is equal to 0. The same root twice. If you want an example here, y prime prime plus 2y prime plus y is equal to 0 has characteristic or auxiliary polynomial r squared plus 2r plus 1 is 0, which is r plus 1 squared is 0. So this says r is equal to minus 1 and also r is equal to minus 1. R is R1 with multiplicity 2. What you want to be able to say, if you were following the first case here, you would love to be able to say, oh, I made the assumption that my solution looked like y is equal to e to the rx. And so this must mean that y1 is e to the r1x, and also y2 is e to the r1x. Because that's what you would do in this distinct case. This actually gets to your question. The problem is, if you check the Wronskian on these, they're linearly dependent. Wronskian is 0 everywhere here. So these are linearly dependent. And I need 2 independent solutions to describe what's happening, not 1. So if I want to extract a second solution, I can't just use the same function twice. I haven't added new information. I'm missing a dimension of information. So I'm going to show you this derivation of where the second solution comes from. And then I'm going to tell you that you never have to do it, and you can just write down the pattern, which is what most of this boils down to. But I want you to see where it comes from. So suppose that I was going to try to come up with a second solution to this differential equation. Y prime prime plus 2y prime plus y is equal to 0. And I already know that the auxiliary polynomial r squared plus 2r plus 1 is equal to 0 gave me r is equal to negative 1 with multiplicity 2. And so I know, at the very least, I know I've got this as a solution. So the approach that we're going to take actually runs through thinking about this thing in that differential operator language. I'm going to rewrite this as d squared plus 2d plus 1y is equal to 0, right? 2 derivatives of y plus twice 1 derivative of y plus y is equal to 0. So it's a symbolic recoding. And that's a polynomial. And so if you take enough math, I can probably convince you that this actually is okay to factor this thing, right? That is a polynomial of derivatives, and so it factors. That's weird, but it works. So what we're going to do is we're going to take this chunk right here, and we're going to call it u of x. So this is like u substitution. I'm going to turn a second order equation into a first order equation by taking all that crap and calling it u. And the result is I get the equation d plus 1 times u is equal to 0. Now let me rewrite that in terms of the original symbols. This would say u prime plus u is 0, or u prime is equal to minus u. And that would mean u is equal to e to the minus x. Well, that shouldn't be surprising because we already found one of those up there, right? I just solved the first order equation here. The second solution comes from undoing the substitution. I know just from the first order equation that u must be equal to e to the minus x. But now, using the substitution, d plus 1y is equal to u, which means d plus 1y is equal to e to the minus x. If you write that out, you get y prime plus y is equal to e to the minus x. Now, way back at the beginning of class, very first thing we did when we were studying first order linear equations was we did integrating factors. Yeah, no one needs head shaking or like sighing out there, right? You learn integrating factors for a reason. We've turned this problem into a first order problem. If you actually compute the integrating factor here, you get e to the integral of 1 dx, which is e to the x. If you go through the process of solving this equation with integrating factors, what you're going to find is that y is equal to c times x e to the minus x plus d e to the minus x. That will be the solution if you do that. Yep.
Is that d different than the d up above?
Oh, I should be careful here. Yeah, we should now use lowercase letters. C x e to the minus x plus d. Yeah, that's not the derivative d. It's just a constant. So what have we just shown? The general solution to the original equation is a linear combination of e to the minus x, which I already knew was a solution, and this new term, x e to the minus x. So this thing right here, if you look carefully at this, this looks like a span. It's the span of e to the minus x and x e to the minus x. So it turns out a second solution to this differential equation, if y1 is e to the minus x, y2 is x e to the minus x. And these are linearly independent. You can check the Wronskian if you like, although it's kind of annoying because you end up taking product rules as these get bigger and bigger. So the idea is this thing that we did here that we derived works generally without derivation. You can always cook up a family of linearly independent solutions to a repeated root just by multiplying by enough powers of x. So if I gave you a characteristic polynomial, or an auxiliary polynomial that looked like r minus 3 to the fourth, and I said, give me a set of linearly independent functions that solves this corresponding differential equation, I guess in this case it would be, I'm not going to write it down, but whatever it is. Yeah, I'm not going to write that down. Then you would know from this pattern generally that the solutions that correspond to this would be e to the 3x, I should say here, this is r is equal to 3 with multiplicity 4. There's the obvious one from the one variable case, and then I just multiply by powers of x until I have enough of them. How did I know to stop there? 4 terms means 4 solutions to go with it. Okay, so generally this is the approach when you have repeated roots. A term of the form r minus r1 to the m has corresponding solutions, I should say corresponding linearly independent solutions. E to the r1x, x, e to the r1x, and then you stop when you get to x to the n minus 1, e to the r1x. The book just asks you to trust that these are linearly independent, right? There's no reason for you to like slog your way into a 10, like the Wronskian of this thing, it's going to require you to take third derivatives of all these functions and then take a 4x4 determinant. I advise against it. Okay, so what that means is that we can handle a more sophisticated set of problems. Y triple prime plus 3y double prime plus 3y prime plus y is equal to 0. Auxiliary polynomial, r to the third plus 3r squared plus 3r plus 1 is equal to 0. And then you go into your library of the Pascal's triangle or binomial theorem or whatever you know from the past and realize immediately that this is r plus 1 to the third. I mean, obviously. So this is r is minus 1 with multiplicity 3 And hence, what I want you to be able to do is just look at that and write down, okay, so the homogeneous solution is C1 e to the minus x plus C2 x e to the minus x plus C3 x squared e to the minus x. Okay, so what are you expected to do in practice? If I don't ask you to derive something, all I'm asking you to do is take the equation, write down the auxiliary polynomial, factor it, and then know how to structure the solutions. All right, questions about this stuff before I go on to my favorite, which are the complex roots. All right. Okay, so the last, and probably for a lot of people the most annoying solutions, is case 3, conjugate pairs of complex roots. So what I mean by conjugate pairs is they will always come together. There will always be two of them in a matched set. And that's where you have AR squared plus BR plus C is equal to 0 boils down to roots that look like R is equal to, say, D plus or minus I times E. The reason that these are going to come, if you have complex roots, they come in plus or minus variety like this, is because we're always assuming that A, B, and C are real numbers. And so the roots have to come in conjugate pairs, or they'd be complex numbers when you multiply it all back out again. So for example, if I gave you R squared plus 4R plus 5 is equal to 0, and you run through that calculation, I guess we could write down the differential equation too. Y prime prime plus 4y prime plus 5y is equal to 0. Auxiliary polynomial. You might realize that this can be written like this, because you really love completing the square a lot, but you should. And so R is going to be equal to minus 2 plus or minus I is what this turns into when you're finished. Okay, so I've got a complex conjugate pair of roots. The trick here is these are distinct. So the same rule applied as applied to the distinct real roots. It's just that the answers now are going to be y1 is equal to e to the d plus IEX, and y2 is equal to e to the d minus IE. I shouldn't be using e twice. I'm sorry. It's dumb. About what's a good set of letters here? I've already used A, B, and C, D, E, F, G, H. Those are functions. How about U plus I times V? There we go. So e to the U plus IV and y2 is equal to e to the U minus IV. Those will be linearly independent solutions. I'm allowed to do exactly the same thing here as I did before. I could write down that the homogeneous solution looks like C1 e to the U plus IV plus C2 e to the U minus IV. And in a lot of fields, this is the acceptable way to do this. If you're an electrical engineer, for example, or you're working control theory or robotics, typically you're totally fine working with complex exponentials. Now, one thing that you might do is you might separate out the real part from the imaginary part. So let me show you what I mean by that. Because there's actually an interpretation of the answer in that way. So for this particular equation here, y prime prime plus 4y prime plus 5y is 0, and you figured out that r is equal to minus 2 plus or minus I. From knowing how the exponential functions work, we can see that the homogeneous solution should be C1 e to the minus 2 plus I x plus C2 e to the minus 2 minus I x. And I noticed that there's an e to the minus 2x in both terms, and so it's not uncommon to write it like this. this e to the minus 2x here was in both terms, and so I can factor it out. The way to think about this as an engineer or a scientist is you can think about this as affecting the amplitude of the solution. This is measuring something about oscillation or vibration. This is a thing that's going like around and around in sort of an oscillatory way. And this is saying how large those oscillations are. So when you're looking at complex pairs or conjugate pairs of complex roots, I want you to think anytime you see that, you are looking at a vibration or a harmonic oscillation. Okay. Now, lots of fields use complex exponentials as the basic object of studying rotations. So there are people that would not bat an eye at this and would say, oh, this is decaying as time goes on because the e to the minus 2x is crushing it to 0. And there's some kind of oscillation that's happening here. I don't know what its amplitude is, but I know that its frequency is 2 pi. You can just read that off the complex exponentials. However, many people that you will work with, who are maybe your boss in various fields, will look at that and say, I have absolutely no idea what an e to the ix means. Can you just turn it into sines and cosines for me? So let's finish this up by turning it back into sines and cosines so we can see the standard form of these, and then we'll start interpreting. So I had you do this on the worksheet last time. If you have e to the ix, you could write that as the cosine of x plus I times the sine of x. So I could take this solution and write it as yh is e to the minus 2x times c1 times the cosine of x plus I times the sine of x plus c2 times the cosine of minus x plus I times the sine of minus x. Cosine is an even function, so cosine of minus x is the same as cosine of x. And sine of x is an odd function, which means the sine of minus x is minus the sine of x. So if you resort this, that's a cosine of x, that's a cosine of x. This is going to be c1 plus c2 cosine of x. This is a sine of x with an IC1 stuck to the front of it. This is a sine of x with a minus IC2 stuck to the front of it. So if you bring those together, you get I times C1 minus C2. And then the cheater move. This is like showing people your dirty laundry. Nobody wants to see combinations of arbitrary constants. You just say, that's a combination of two arbitrary constants. Let's just call that D1. And here is a combination of two arbitrary constants that I've multiplied by I. I'll call that D2. E to the minus 2x, D1 cosine of x plus D2 times the sine of x. That is the more standard way of writing the solution to an equation that has complex roots. And now we can really see that the solution is built out of an oscillating part. This is sort of a periodic part, and a part that is an amplitude section. So
the D2 includes the I?
It does. In fact, this is a good question here. Really, I didn't tell you, but the C1 and C2 we wrote down right here, these are complex numbers. In fact, the C1 and the C2 are complex numbers that are complex conjugates of each other. They have to be, because otherwise I'd get complex values out of this thing that's supposed to be describing a real scenario and it can't spit complex numbers out. So, because they are complex conjugates, when I add them, I delete the imaginary parts, and when I subtract them, I delete the real parts. And so if I have an imaginary number times I, the i's disappear. Now that might seem like I'm pulling a fast one on everybody, but it is the case that these numbers are real valued numbers. You can tell just from the sort of post hoc justification is they must be real because this is describing this is the sort of equation that shows up when you're studying a mass spring system. Mass spring systems don't suddenly pick up and start oscillating in the complex direction. Like, they don't just disappear because they're like, oh, I'm imaginary for a while, right? So these numbers had better be real numbers, or they're talking about rotations that we can't even see. So if you actually trace through the math here, which I would do, if you take 344, I'll actually show you more of the structure of how these things work. These have to be real because these numbers are structured in such a way that when I add and subtract them, all the complex numbers just disappear. Now, let's suppose we plot this for a second. This is a specific solution to that differential equation. So what the e to the minus 2x does is it decays. E to the minus 2x is a function that kind of looks like this, right? And then there's going to be a minus e to the minus 2x, which looks like this. And this thing, when I take two different sines and cosines that have the same frequency and I put them together, the result is a sine or a cosine with a phase shift and a different amplitude. So these things together represent a single oscillating sine wave with possibly a phase shift. But the amplitude is controlled by this exponential. It can never be larger than this. So what you get is an answer that looks like this. The exponential term is forcing the oscillations to go to 0. So in practice, this is what would be called a damped oscillator. You can think about shock absorbers in a car, right? The spring wants to do this forever in your car, but the shock absorber damps the vibrations, which takes all the energy out of the oscillations. So this is an example of what we're going to study in 8.5, which is a damped mass spring system. That term right there, that 4y prime, basically imposes this decay. It forces the oscillation to collapse to 0. Just by point of comparison here, we should think about an equation where that's not there. Like, if I just left that term off, y prime prime plus 5y is equal to 0. This would have characteristic r squared plus 5 is 0. So r is equal to plus or minus I times the square root of 5. And that would have a solution that looked like c1 cosine of root 5x plus c2 sine of root 5x. Notice here what happens is there is no decay in this case. The amplitude of this is always fixed. That term that drove this to 0 is not there. So if I take out that middle term, my solution just oscillates forever. You can think about this as an ideal mass spring system or an ideal pendulum, right? I just pull it out and let it go and it just wiggles forever. No friction, no damping. The solutions to this just go forever. All right, so let me be concrete now about like what the general situation is. So if ay prime prime plus by prime plus cy is equal to 0 has roots r is equal to roots to the auxiliary polynomial. R is equal to u plus or minus iv. Then the homogeneous equation yh is going to look like one way of writing it would be c1 e to the u plus ivx plus c2 e to the u minus ivx. If that is this choice in your field, for us, almost always what we're going to be doing is writing c1 e to the ux cosine of vx plus c2 e to the ux sine of vx. They come in matched pairs, so they produce matched pairs of solutions. And again, I just keep hammering away. Complex roots correspond to vibrations. Yep. Nope. Because it's hidden in there somewhere, right? The I is in there. It's all part of the mix. Again, for practice, in the derivation, the I's are going to be running around and they're important. But the way people work in this in practice is complex. Just immediately think, oh, complex roots, sines and cosines. Yeah. I mean, that's why I put or right here, right? These are arbitrary. Yeah, this C1 and C2 are not the same as this one and C2, but they're both arbitrary. And when you give me an initial condition, if I gave you an initial condition here, it will produce different values of C1 and C2 than if I gave you an initial condition here. All right, so what that means is, now you're all fired up. I know everyone's all fired up all the time. You can tell. Everybody's got their week 8, like I'm as excited as I've been the entire academic year. Like day 1, I got the same juice. Okay, so y prime 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 plus y is equal to, plus y? No, minus y is equal to 0. Somebody comes along and gives you that. And you auxiliarize it first. R to the 4th minus 1 is equal to 0. How many solutions should be part of the solution set to this thing? 4. 4th degree, 4 solutions. Now you put on your factoring hat, and you write this as r squared minus 1 times r squared plus 1, because it's a difference of squares. And in your earlier mathematical life, you would have written this as r plus 1, r minus 1, times r squared plus 1 is equal to 0, and called that an irreducible quadratic. But that's illegal. There are no irreducible quadratics anymore. Everything can be factored all the way. R plus 1, r minus 1, r plus I, r minus I is equal to 0. And from there, you just read off the solution. The homogeneous solution should be C1 e to the minus x from that term. C2 e to the positive x from that term. This is purely imaginary. So that formula tells me that this bit with the e to the ux's is not going to be here because u is equal to 0. So we're going to get a C3 cosine of x plus a C4 sine of x. There's your solution. Now you might get the impression this is actually pretty easy once you know the theory, right? Like you just factor the polynomial and look at the roots down. And in fact, by comparison with linear algebra, yeah, this is a lot easier, right? Just memorize the pattern and like factor the polynomial. The hardest part about doing this is factoring the damn polynomials. So maybe I'll come up with some cute ones where you have to use like grouping or something, or like the rational root test to... No? Well, the book might expect you to do that. So generally, I will say that the reason that we restrict ourselves to the lower order equations is because the higher order ones are hard, right? It's hard to factor, unless I just give you the factored equation. The big question that we've left off here, and if you're going to read ahead in the book, I'm going to suggest that you don't. Because what we have left off is, what happens if there's something that's not 0 over here? So the book goes through a really beautiful method called the method of annihilators, right? Where you come up with this really elegant theoretical approach to how to do it, and everything is clearly understood why we're doing all the steps we're doing. What we're learning is the applied mathematics version, which is you guess. So if I write down y prime prime plus y is equal to x plus e to the 2x, and I would like to know a function that would produce that thing, I look at that and I say, I'm going to guess that what went in, I'm going to guess that the input that went into this side to produce that output is ax plus b plus c times e to the 2x. And then I grind out a giant system of equations to figure out the coefficients that made it happen. This is called, it's got the fancy name, the method of undetermined coefficients. But what it really is you look at the output and you eyeball what the input must have been. So that's 8.3. We'll do that next time. We'll do some problem solving. And then the real beautiful part of this for me is going to be if we can look at the mass spring system and start understanding how these damping forces the damping comes into play, what the function over here corresponds to in a physical system, and then we'll also talk about harmonic resonance, which I think is really interesting. So, all right.